So I think Samrat's probably the only person who knows what's going on now, so I'll pass over to you.
Thanks, Professor Dobson, for chairing the session, and all the speakers for a spectacular session on amyloid. So this brings us to the last session, special keynote session by Professor P. Balaram from IISc Bangalore, Indian Institute of Science, Bangalore. I have been closely mentored by Professor Balaram during my PhD and later on. So I'm quite excited that he has accepted my invitation. And while working on some aspects of IDP for the past 4 years, we have been looking at conformational dynamics, and we are quite fascinated about looking at dihedral relaxation in intrinsically disordered proteins, and then we looked at some really intriguing conformational dynamics, the phi-psi conformational space, and I was really fascinated about that, and I thought that this will be a great occasion for Professor Balaram, who was a colleague of G N Ramachandran for a long time, so to talk about G N Ramachandran tonight. So Jayant is going to chair the session.
So Samrat told me a short time ago that I have to talk at least 5 minutes about Balaram. So now I first encountered the name Balaram, this Balaram, within a few months of my starting my postdoc at Stanford in 1986. There was this postdoc from India working in one of the chemistry labs. The NMR at Stanford was shared by 4 labs. And this lady was in complete awe of this person called Balaram. And I had come, as I'd mentioned earlier, from a lab which did neurochemistry or neurophysiology, and I had not heard of his name. So anyway, after a year and a half, I decided to visit the Indian Institute of Science in the molecular biophysics unit where Balaram was, and I met him there for the first time. And he was extremely gracious. He spent perhaps 3/4 of the day taking me around the department, the molecular biophysics unit, taking me around Bangalore, at least a region outside the institute, taking me for lunch, taking me to his house, etc. And that's when I really found out that he is a remarkably good human being. I then applied to the molecular biophysics unit in the Indian Institute of Science. They didn't give me a job, but that's another story. I'm not sure how much he had of a say in that decision. But in any case, so then I joined the Tata Institute of Fundamental Research in Mumbai and then moved to Bangalore 3 years later to set up the National Center for Biological Sciences. And that's when I started meeting Balaram often. And this was usually in various conferences where invariably I would have to talk after him. And once you hear his talk, you will realize what a big handicap that was. Balaram is a superb speaker, has superb style, and it's very difficult for someone else to speak after him. So anyway, Balaram is a chemist by training. He did his undergraduate studies in Pune, where I am right now, where I work now. He did his master's degree in chemistry at the Indian Institute of Technology, Kanpur, and a PhD a very quick PhD at Carnegie Mellon, after which he did a 1-year postdoc at Harvard. His work in the US was really important stuff. I think it was one of the first demonstrations of negative NOEs in biomolecules. He came back to India, started working on lipid membranes, and finally graduated to looking at peptides, peptide membrane interactions, and that's what he's been working on since the early 1970s. He's played a major role in Indian science, both by being the director of the Indian Institute of Science for nearly 9-10 years, and also as the editor of a very influential science journal in India, Current Science, where he's made incisive comments about all aspects of science policy. He stopped doing that once he started being part of the establishment. But then I think towards the end he went back to being, writing editorials there. So it's with great pleasure that I've accepted this, to chair this session, and here's Balaram.
Thank you, Jayant. I must thank Samrat for inviting me to this conference. I think the only qualification I have to speak to you is that when Samrat was doing his PhD, I dissuaded him from working on proteins. And subsequently, I think he's made a wonderful career for himself working with proteins. I've always worked with peptides and proteins which were ordered, and I was apprehensive about coming to a conference which was primarily devoted to intrinsically disordered proteins. But after listening to a day of lectures, I find that there is considerable order in the field of disordered proteins. And eventually, disordered proteins seem to be going towards those beautiful all beta sheet structures which have been pictured on slide after slide. But my task today, assigned to me by Samrat, is to talk about Ramachandran and his work, which was done a little more than half a century ago in Madras University in India. That's a picture of Ramachandran looking at the blackboard. He was a formidable professor, and that's the Ramachandran map, which you will now see in all biochemistry textbooks. Ramachandran died in 2001. He stopped working in the field of peptides and proteins in 1979. He retired maybe around 1982 from the department and lived on for almost 20 years, where he did a little bit of work on mathematical logic, but he did not return to proteins. Although Ramachandran was alive, he did not really appreciate the kind of impact that the field of structural biology, the transformation that took place in structural biology, and the impact that his own work had. What I would like to do this evening is really to tell you a little bit about the history of the Ramachandran map, the early work of Ramachandran on collagen, which led to the map. But what really triggered me was some years ago, I spoke about this at a conference organized by Jayant at the National Center for Biological Sciences. Just before that, I had read this article by David Eisenberg, which appeared in the Proceedings of the National Academy of Sciences of the United States in 2003. This was an article by Eisenberg, and this issue of PNAS was actually celebrating Pauling's triumphant structure, the alpha helix, about 50 years after the helix had been proposed. And there was this paragraph which said that today the Ramachandran diagram is taught in all classes on protein structure and is featured in every textbook to give insight into the forces that determine the structure of proteins. But then he added this dismissive sentence, but there is nothing in this diagram beyond what Pauling and Corey knew well. They built models of their proposed structures that embodied all features of the Ramachandran diagram. Apparently, they understood the principle so well that they felt no need to explain them by a diagram of the sort. This sounded somewhat strange to me, so I thought I must go back and once again study the early origins of the field of protein structures. Let's turn to 1943. We heard of Huggins and Florey in the morning, and there's Huggins once again. He was a polymer chemist, but also worked on polypeptides, and probably wrote, I think, probably the first and most important review on hydrogen bonded structures in proteins in Chemical Reviews in 1943, where he drew pictures of hydrogen bonded chains of this type. The only thing that Huggins did not know at that time was that peptide bonds were planar. This is something that Pauling knew later, and eventually the Pauling helices are very close to the Huggins helices of the 1940s. And there is this wonderful paper in 1950, and I think I must say this with Professor Dobson in the audience. The paper published in the Proceedings of the Royal Society, and as far as I know, this is the only paper which I've seen in the literature in which all three authors have received the Nobel Prize. But this is also the only paper in the literature of protein science which I've seen where probably every single hydrogen bonded structure which is there in the paper is wrong. And this was just before Pauling got it all right. That's a picture of Pauling with a model of the alpha helix at Madras in a conference organized by Ramachandran in 1967. By this time, Ramachandran had finished both his work on the triple helix of collagen and had also produced the Ramachandran map, and Pauling was in fact the president of this conference. But let me go back to the early 1950s. In the early 1950s, Ramachandran went to Madras University, which is one of the oldest universities in Madras, to start the Department of Physics. He was a student of the Indian Nobel laureate, C.V. Raman, who was professor of physics at the Indian Institute of Science, where I worked throughout my academic career. Now, Raman joined the Indian Institute of Science as a student of electrical engineering. And he used to stand in front of our physics department every day waiting for Raman to come in. And he wanted to do physics. And after Raman had talked to him a few times, he called the professor of electrical engineering and told him, Ramachandran is too bright to be an electrical engineer, so I'm admitting him to the physics department. Raman never endeared himself to his colleagues at the institute. And Ramachandran then became his student and began his work in the area of optics and also in the area of the optics of crystals. After completing his PhD at the age of 29, Madras University was starting a physics department, and they asked Raman to become the professor of physics there. But Raman said, I've already retired, I can't be a professor anymore. Why don't you take Ramachandran? So in an unprecedented move in India in those days, at the age of 29, he was a full professor and head of the physics department, and he was to start a research department of physics. A question, of course, is what do you do if you start a research department of physics in 1951 in a university where there are no facilities? Which area of physics should you actually start on? And I think Ramachandran made an inspired choice. He'd already worked for a little while in the early days of crystallography on diffraction. So he decided to set up a department of what he called crystallography and biophysics. And what structure should one take up? He did not know. And it so happened that J.D. Bernal, one of the most influential figures, I think, in protein science, because it's the Bernal-Crowfoot paper which really began protein crystallography in the 1930s. Bernal arrived in Madras, and Ramachandran asked Bernal, what do you think I should do? Bernal said, you know, I'm not happy with the structure of collagen. There are many structures of collagen which were at that time around in the literature. But where do you get collagen? Next door to Madras University was India's newly formed Central Leather Research Institute, where they were extracting collagen from rat tail tendon. And so Ramachandran got a sample of collagen, and then along with Gopinath Karta, who I will mention very briefly, they produced this diffraction pattern. And once they produced this diffraction pattern, in those days it was fiber diffraction which really determined the structures of fibrous proteins. The alpha helix was the first structure. In fact, Max Perutz, immediately after the Pauling proposal, Perutz detected the helical diffraction spots in a sample of keratin. Ramachandran deduced the triple helical structure of collagen, and I will tell you a little bit about collagen. But a word about Gopinath Karta. Karta was Ramachandran's postdoc, and the two of them together produced the structure. But Karta was also the first person to solve a crystal structure in the United States. He did the structure of ribonuclease with Wyckoff and Richards at that time, and was an extraordinary crystallographer. Collagen, of course, is the large fibrous protein, has an unusual amino acid composition. Today, we would probably call large sections of collagen as low complexity repeats. These phrases had not been discovered yet in those days. So it was simply a protein which had a repeat structure of glycine, proline, and hydroxyproline over much of its sequence. And the most interesting thing here was 1/3 of the amino acids in collagen were really glycine, and it was present at position 1, at position 4, and so forth. So this immediately tells you that there must be some kind of threefold structure in collagen. Pauling had already thought of triple helical models, but like Pauling's model of DNA, the triple helical models that Pauling thought of were actually wrong. I don't know how many of you have seen Pauling's famous model paper in the Journal of the American Chemical Society on the structure of DNA, which has all the phosphates on the inside. So there was difficulty at that time in thinking about structures which had more than one chain. And this was, in fact, the crux of the problem. But those of you who've seen fiber diffraction photographs will realize that there's very little data from which to determine a structure. Structures then required model building, and more than anything else, they required intuition and insight. Here then are the early pictures of Ramachandran of the triple helix viewed down the helix axis. This was in the days before computers. These were projection diagrams drawn by hand, and the triple helical structure eventually was the structure that I show you here. These were models built in my own department in the 1970s when I had just joined, and they were made of these pieces, sometimes made of wood, sometimes of metal, which were all joined together. And you can see those water molecules there, I'll come back to them later, which actually hold the collagen chains together. These are the Ramachandran papers in Nature. You can see 1954, 1955, 1956. And at the same time, there's the structure of collagen paper of Rich and Francis Crick in 1955. The thesis of the Francis Crick paper really is what triggered Ramachandran's work on the stereochemistry of polypeptide chains. Crick simply said that the Ramachandran structure is wrong. And the reason the Ramachandran structure was wrong, according to Crick, was that the atoms came too close to one another, and therefore the structure would be an unstable structure. But at the time this was 1955, you must remember that nobody really knew how close atoms should come to one another. The van der Waals contact distances between atoms had not quite been established. There were some distances available in the literature, but there were almost no systematic studies of how close atoms come to one another in crystals. But of course, Crick was already by then an influential man, having determined the structure of DNA. And therefore, I think this was a major blow to Ramachandran. Working in India as a young man, unknown, in an unknown university, it turned out that criticism coming from Cambridge was in fact taken very seriously by the surroundings. And I will show you then a picture of what Ramachandran's group looked like, because I'm going to come back to the way in which India has transformed over the years. This is what graduate students used to look like in those days. And there was the formidable professor, the only man wearing a tie. And this was the group in 1955. Now this was Ramachandran on collagen some years later, and he said that how important the nature of helices were in protein structures. And he describes in this article written in 1988 how J.D. Bernal really suggested that he work on this problem. These then are the pictures of the three helices which had by then appeared in the literature in the mid-1950s. The alpha helix, the DNA double helix, and the collagen triple helix. It's always instructive for students to go back and ask the question, how were each one of these helices actually determined from the minimal data that was available at that time, and which structure would have been the more difficult to postulate with the data that was around at that time. In my view, I think the most difficult of the structures, technically the most difficult structure, was in fact the collagen structure. Watson and Crick were tremendously helped by the Chargaff rules, which allowed the 80 GC base pairs to be placed in the middle of the helix. Pauling did write about collagen, and he suggested that he'd given a wrong structure, and Pauling was proposing a stochastic model for the determination of, for proposing structures, and he said you should be allowed only one chance, but since Pauling and Crowley now are proposing a new model, they should be allowed a second chance. But before they guessed the second structure of collagen, the Ramachandran papers were also there, and you can see what Pauling says here. He says, although I may have some feeling of regret that Corey and I did not succeed in making our second guess, he said that the problem was a very difficult one. And it is truly, even today, if you look back at the work, a truly difficult problem. What did Crick say about collagen? Years later, when Crick wrote a book, he said this, all about collagen, and he says the characters were just as colorful and diverse. The facts were just as confused and the false solutions just as misleading. Competition and friendliness also played a part in the story, yet nobody's written even one book about the race for the triple helix. This is surely because in a very real sense, collagen is not as important a molecule as DNA. And but then he goes on to add that before he started working on collagen, Alex Rich and he said that after all, there's no collagen in plants. In 1955, after we got interested in the molecule, we found ourselves saying, do you realize that 1/3 of all the protein in your body is collagen? And therefore, you can see that he goes on to say that DNA is, of course, more central to biology. And so, as I've said before, it is the molecule that has the glamour, not the scientists. This is not something that I would entirely agree with, because sometimes it also turns out that it's the scientists who have the glamour very often. Is the Ramachandran collagen model right, or is Crick right? It turns out that in 2012, a single crystal structure of a large collagen peptide was determined by a Japanese group. And it is in this paper that he refers also to a paper of Ramachandran early on in the 50s in Current Science, where in fact various models of collagen were produced. But the conclusion then is that the structure of collagen does not correspond to the Rich-Crick model, but instead to the triple-stranded 7-2 helical model, which was the model proposed by Ramachandran in 1954. But the Crick criticism that the Ramachandran structure is wrong because atoms come too close to one another was what drove Ramachandran to look at the stereochemistry of polypeptide chain configurations in this famous paper in Journal of Molecular Biology. Now, it turns out that the question that he asked was, how close can atoms come to one another? What are the van der Waals contact distances? By this time in the early 1960s, there were enough crystal structures of small molecules to look in the solid state structures to determine how close atoms can come. So a table of contact distances were made, and the very simple steric contact idea was imposed. That is, two atoms cannot occupy the same place at the same time, so if they come closer than the sum of their van der Waals radii, those conformations must be disallowed. But how then does one describe the conformations of polypeptide chains? He described them in terms of the two dihedral angles about the N-C alpha bond and the C alpha CO bond, and then asked the question, what are all the conformations of phi and psi, all the values of phi and psi for which allowed conformations are generated, and what are all the regions of phi psi space which are disallowed? But there were no computers at that time in the early 1960s in India, and the first calculations were actually done with this calculator by my colleague of many, many years, now retired, Professor Ramakrishnan. In 1967, he was a young man, and by this time he'd already done this work and got his PhD. And this had 4 basic arithmetic operations. It had no memory location, and some of Ramakrishnan's calculations were also done simply by hand. I'll show you a picture of him much later, post-retirement, where I think at IISc in Pune, where Jayant is now the presiding deity, Ramakrishnan some years ago did conduct a course where he was teaching students how to calculate the dihedral angles by hand, given the coordinates of 4 atoms. But since Professor Peter Wright is here in the audience as the editor of the Journal of Molecular Biology, I must point out that in the 1963 paper, famous Ramachandran paper, the legends to the 2 most important figures in the paper were interchanged. But nobody ever pointed this out. So once when we were trying to bring out a special issue of Current Science in 1990, to felicitate Professor Ramachandran, I asked my colleague Ramakrishnan, can I now put in a correction when I reproduce this paper? But he said, no, don't do this, because Professor is still alive and he will get very, very angry. And so I let it pass. But I show you this in 2012, I did make the correction, and the 2 legends are interchanged, but the famous Ramachandran diagram actually has the wrong legends in the original paper. This actually tells you that much of the time, nobody ever reads the original paper. When did the Ramachandran map acquire its name? It acquired its name in 1969, when Dickerson wrote this book along with Irving Geis. And I think this is the book that everybody should see, because this is the first time that anybody really got an idea of what proteins look like, simply because of Irving Geis's wonderful representations of proteins. A marvelous artist, and without him, I don't think anybody would have found what hemoglobin looked like. Max Perutz himself said once, he searched for the truth, and then he said, could the truth about protein structures really result in such a hideous object? And the beauty in protein structures came many years later, when I think Jane Richardson began to draw the ribbon diagrams, and everybody began to see how proteins actually fold, and computers helped us. But that's the Ramachandran map in '69, and you can see what it looks like. But there's an interesting comment in the Dickerson book, because the dihedral angle values were being changed. From a scale which went from 0 to 360, it was being changed from minus 180 to plus 180. So I think we were all confused in the early days. Even in the 70s, we used to be confused. And he said that another shift is being considered by the Commission on Biochemical Nomenclature. This will achieve consistency with the usage of organic chemists, but will make the literature virtually unreadable. But I think a new generation learned how to read the literature. But he says, according to the traditional sources, there are 2 types of sin: sins of omission and sins of commission. And this is most definitely a sin of commission. Because I remember in the early days when I came to the department and didn't know anything about the dihedral angles, we used to have some people talking in one convention and other people talking in another convention, and Ramachandran invariably used to get angry. And the Geis diagrams also tell you the manner in which Pauling himself would have actually come across the alpha helix, the way he describes it. And the Geis diagrams actually are drawn that way, so this is a wonderful book. But then what is the Ramachandran map? It allows us to envisage islands of allowed structure for the polypeptide backbone in conformational space. What else does it do? It transforms an essentially 3-dimensional problem into 2-dimensional space where we can think about it. The 2 axes now are the dihedral angles or the torsion angles, and the 2 axes are 3-dimensional parameters. And therefore, transforming a 3-dimensional problem into 2 dimensions allows you to think analytically about secondary structures in polypeptides. The Ramachandran map has undergone many transformations. This is an early version. This is a later version, and you can see the quadrants are changing as the scales change. This is yet another version which appeared in the Journal of Molecular Biology. And then you can see this is the version which appeared in a famous review article in the Advances in Protein Chemistry in 1968. The importance of Ramachandran's work was recognized early by John Etzel at Harvard, who invited him to write a review article in Advances in Protein Chemistry. This is a very long article. It runs to almost 150 pages. And in 1988, I spent a few weeks at the University of California in San Francisco. And in the library of the Department of Biophysics and Biochemistry, the department had a small library. They had Advances in Protein Chemistry. So I went there and picked up the volumes of protein chemistry, and I would be looking through them. I found Ramachandran's article. Surprise, it turned out that that article of Advances in Protein Chemistry was the most mutilated article in the collection which were there in the library. Because I think generations of graduate students who were taking some course or the other had actually pored over this article. This is an important article. Not read very much nowadays, highly cited, but sometimes worth reading once again. But there is this little editor's note, which says, by the author's request, the publishers have left certain matters of usage and spelling in the form in which they wrote them. This immediately tells you that Ramachandran was a formidable man. Even the editors of the Advances in Protein Chemistry, John Etzel, couldn't get him to change the way he wrote things, and they couldn't get him to change his spelling to the kind of spelling used in America then. I guess in the late 1960s, America was not as influential as it is today in changing spelling. The evolution of the Ramachandran map is shown here. Today we have all these colored maps. You can get them on Google. But I'll return to the question which David Eisenberg really raised. Did Pauling really understand this very well? Those of you who've seen the original Pauling papers will realize that Pauling always gave his coordinates only for polyglycine. He never gave any coordinates for an optically active amino acid. And I found this article on Pauling's left-hand. So the helix coordinates are all left-handed helix coordinates. But for glycine, it doesn't matter because it's an achiral amino acid. Jack Dunnett wrote this article in 2001. He says, a few months after the publication of the Pauling structures, Morris Higgins noted that for amino acids with the correct absolute configuration, then he adds there that he was already aware of the barefoot result that a left-handed helix would lead to a distance of only 2.64. He concluded that the levo-polypeptide forms right-handed spirals and dextro-polypeptides form left-handed spirals. This, of course, is evident from the Ramachandran map when you look at the Ramachandran map for L amino acids and for D amino acids. So you will find the left-handed alpha helix there, the right-handed alpha helix over here. So it's quite clear that Pauling was looking only at the backbone. He ignored the side chain, and therefore conformational space for Pauling actually was the conformational space for the glycine residue and not for the other 19 amino acids. The Ramachandran map has been most widely used by crystallographers in later years to actually ensure that protein backbone models are correct. You can see an incorrect model as late as 1988, 25 years after the Ramachandran map. And if you have a correct model, this is what, there are many articles in the literature on errors in 3 dimensions. They continue to come even today. Brian Matthews wrote many years ago in Current Science an article showing an incorrect model of lysozyme and a corrected model of lysozyme once you had interpreted the map correctly. This is a distribution of phi-psi values now from a very large number of proteins. There are over 427,000 amino acid residues. This would be an experimental description of Ramachandran space in high resolution protein structures solved at a resolution of less than 1.5 angstroms. You can represent the Ramachandran map in wonderful ways now because of all the graphics which is now available. I show you one version drawn by a young student of mine, which actually tells you how these are populated. It's a transformation here. You can see the regions in which you're most interested. The polyproline 2 regions, the beta sheet regions are here. Much wider range of distributions here. The alpha helix very much narrower in the range of phi-psi values. But since I am speaking in a conference where amyloid fibrils have occupied so much attention, I thought I would show you a structure. This is a structure which I was attracted to simply because of its beauty, and I believe this is also the last paper that Max Perutz wrote. And this is what is called, he said, amyloid fibers are water-filled nanotubes, and drew this wonderful structure. And what would a nanotube look like? That's what it would look like. And you can see that this is the Perutz structure now generated using 17.4 residues per turn. It's not a helix formed by just one residue repeating itself, but it is a helix formed by two residues repeating themselves all the way around. And it's a wonderful helix with a big hole. The backbone itself, I will show you what phi-psi values the backbone would take. They would take values in that region of the Ramachandran map and in that region of the Ramachandran map. So you would just repeat it again and again, the dipeptide, to generate that wonderful structure. Nature also does this. Nature does this in the beta helices. And in the beta helices, you have these beautiful pictures. You can understand them very well if you use the Ramachandran angles to do this. I'll show you just one example. These are leucine-rich repeat proteins. They're not intrinsically disordered, but they lack the hydrophobic core of globular proteins. And they are, in fact, waiting for a large ligand to come along and bind to them. And they're beautiful structures. Some are horseshoes, some are a little bit flatter, and so on. What are the repeat units? The repeat units here are approximately 20 to 22 residue repeat units. They are repeat units rather like the Perutz nanotube, except that was a regular repeat of 17.4 residues. This, on the other hand, has other little secondary structures in it, and it's got large loops. But it repeats with great order, so that you have many such units linked together. How does it do that? It does that because it has a specific distribution of amino acids along the sequence, along with a critical asparagine residue. Now, if you look at the critical asparagine residue, you will find it makes many hydrogen bonds which pull the different parts of the structure which are to be put together, and it forms every possible hydrogen bonding site on asparagine is actually occupied. But then, where is this asparagine? What is its conformation? In Ramachandran space, it comes in this region, which is a very sparsely populated region, and it is an unusual Ramachandran angle. It has unusual Ramachandran angles. Nevertheless, they are allowed Ramachandran angles, and any energetic penalty that it has to pay has been compensated by this entire network of interactions. I show you that just again, and then if you go back, you can place that asparagine residue in the middle, and then you can develop the sequence repeat. This will not only be a sequence repeat, it will be a conformational repeat as you go along. The conformation of each one of these residues can actually be, but the central tripeptide motif will have a P2 conformation, a left-handed helical conformation, and then the unusual asparagine conformation. We are used to thinking of regular structures in terms of conformations in the helical region, conformations in the beta sheet region. But you can generate regularity out of apparent irregularity in small peptide segments as long as you repeat them sufficiently. You can understand this better by plotting each residue's distribution in there are many, many repeats. You can do this. And eventually you can in fact look at repeats in terms of the Ramachandran conformations that they actually occupy at each single amino acid residue. I believe the Ramachandran map is in fact important, and I think a great deal of work which has happened afterwards has depended on the use of dihedral angles. Sometimes we do not think of how important thinking in torsion angle space really is. Today, if you look at the advances in molecular dynamics, or in the use of molecular dynamics in crystallographic refinement or the refinement of NMR structures, it turns out that all the minimizations, all the fittings, really done by varying structures in dihedral angle space. If you varied structures in Cartesian space, each atom moving its x, y, z, that is a much, much more computationally inefficient process. So you really treat the peptide bonds more or less invariant, and they're just joined by a hinge, and you vary the dihedral angles alone. Now this slide really tells you about Ramachandran in the age of scientometrics. I don't know how it is at Cambridge or Harvard or Berkeley, but it turns out that in India, China, and I suspect many other countries, there is an unreasonable interest in the number of times that a paper has been cited, and sometimes an unreasonable interest in what the H index of an individual scientist is. And Ramachandran, of course, never knew about any of this. And so I asked the question, what would Ramachandran be in the age of scientometrics? So what a colleague of mine helped me to do is to very quickly look at the literature in the Web of Science from about the mid-1960s when the Ramachandran papers appeared. This is the Journal of Molecular Biology paper. This is the Review in Advances in Protein Chemistry. And you can see they've been cited enormously. They have about 45 citations in the years in the 1970s. They keep going up to, that's where the new millennium started, and they're still going up. And for some strange reason, the Journal of Molecular Biology paper has now overtaken the Advances in Protein Chemistry paper. I rather suspect that this is because some influential persons put it into his list of references, and everybody else copies from that list of references. If you look at the Advances in Protein Chemistry, you will find several mutations of the reference. And some of those mutations are quite highly populated. And this really meant that neither the professor nor the student actually looked at the page numbers in the original paper, but they copied it from some other paper. And this is a very interesting paper in the Biophysical Journal in 1965. This, I think, is probably one of the most important papers in the field of peptide conformations, because this is where the details are given. And you can see that it's a very highly cited paper after some time. One might ask the question, if you were a spectroscopist, is there a shoulder there and a peak there? And what is the reason for the shoulder and the peak? There must be some other change happening in the field of protein science. What are those changes? If you go back to the literature and ask, what do you think those, you will find that if you've been around as long as I have, I've seen the literature transform. When the Ramachandran map appeared, there wasn't a single protein structure available. Perutz's hemoglobin structure was at low resolution. Kendrew's hemoglobin structure at 2.8 angstrom resolution was the only structure which had just then appeared. And since there was no email and no telephone and everything, no coordinates came from Cambridge to Madras. It is really because one synchrotron radiation came, and there's been an explosion of protein structures. The PDB has expanded. The PDB requires validation, and therefore more and more people use the Ramachandran criteria automatically for validating protein structures. The second is the explosion in molecular dynamics. Molecular dynamics calculations, if you look at the results of molecular dynamics calculations, not at those pretty pictures which appear on slides, where you can't make out anything from the picture. If you're looking at a conformational trajectory, you're really looking at the variations of the dihedral angles as a function of the time of simulation. And therefore, I think that explains why these papers are still important. But I will show you one paper. This is a very important paper which appeared in Biopolymers, spelling is wrong here, Venkatachalam in 1968. Venkatachalam was Ramachandran's student, and this paper appeared with only his name. It turns out that when this paper, 4 papers were written in 1968, and my colleague Ramakrishnan confirmed this to me a few days ago when I called him up and asked him, is this true? He said, I was there. Ramachandran got these papers all onto his desk, and he was in a very bad mood that day, and he took a pen, he would hold it like this when he was angry, and he scratched his name out of all the papers. And Venkatachalam's paper on the beta turn, this is in fact the paper which examined all the possible allowed conformations of linked peptide units, 3 linked peptide units, to give you the beta turn. And you can see it's very, very highly cited too. Many, many papers appeared from the Ramachandran laboratory in those days which were highly cited. Ramachandran did other work which was far ahead of his time. He wrote a fundamental paper on anomalous dispersion just around the time that Barefoot wrote his paper on anomalous dispersion. In fact, anomalous dispersion was an area which started in Bangalore, independent of other places. Professor Ramaseshan, who later took anomalous dispersion to Dorothy Hodgkin's lab when vitamin B12 was being sold, really contributed enormously in the early years of crystallography. But what is not known very much is that in the early 1970s, Ramachandran wrote a paper in the Proceedings of the National Academy of Sciences of the USA on image reconstruction, the reconstruction of three-dimensional structures from from a succession of two-dimensional images. This paper is in fact fundamental to both computer-assisted tomography and also to later magnetic resonance imaging. And in sort of preparing for this lecture, I asked myself the question, what is the most recent reference that I can find to Ramachandran on the internet? And not the references to the old papers. And you will find that the taxman is the only one I could find. I found that the name Ramachandran is not known not only in the field of structural biology, but it's also known in India in the field of tax law. In the late 1970s, Ramachandran, just before he retired from our department, Ramachandran went to the National Institutes of Health. He spent a year there. He earned some dollars. We all used to earn very little in those days in India, and the only way was to go to the United States, earn dollars, come back, and get those dollars converted into rupees. But then, when you did that, the people who took tax from you would be after you. And so they took away a lot of Ramachandran's tax, and I believe he decided to get his money back. So he went to somebody who then filed a case. And this case was fought for many years, and eventually the judges ruled that it was a fellowship, a scholarship, and therefore the income tax department must return the money to Ramachandran. I don't know whether he ever got the money back, but I think this was the last reference that I found to him as far as India was concerned. Some years ago, when I had the opportunity to produce a stamp marking the centenary of the Indian Institute of Science, I managed to smuggle in Ramachandran's picture into a corner there, and you can also see the triple helix vaguely in the background, because he was probably one of the most distinguished students of our institution. I show you a picture from the old days of the 1967 conference, where both Linus Pauling and Dorothy Hodgkin were present, and that was Ramachandran in 1967. But an interesting feature of this conference was that I asked myself the question, can I find anything on the internet about what Pauling had said at this conference, or did he write to anybody? So I went to the Pauling archives, which are available on the internet, went to the year 1967, and then I found this very interesting letter written by Pauling's wife to her son, Peter Pauling. And she said that they were having a very good time in India, etc. She said, we've been having a busy time. It's interesting too. I really can't see any future for India unless they change drastically. It is sad. The women do a lot here. Now, since many of you have come from abroad, and there are many of you who are too young to know how India was in 1967, the only thing that I would leave you with is that in 2017, 50 years after this letter was written, you must really exercise your judgment to see whether India has changed, Second, whether India has a future. And I think the only true statement in this letter is that the women still continue to do a lot here. And I've come to the end of my presentation, but I will now tell you, since Samrat said that I was a colleague of Ramachandran's, I must end on a personal note. In 1973, when I was still a postdoc at Harvard, I applied for a job in Ramachandran's new department, started at the Indian Institute of Science. And I was fortunate to get the appointment. And I suspect that I got the appointment largely because I worked for a flamboyant supervisor, R.B. Woodward. And what Woodward did was he wrote a long recommendation letter and then sent it off by telegram in those days. So if you received a long telegram in India, you would assume that it's very important, and so I guess they hired me. And Ramachandran then arrived at the University of Chicago to spend the summer there, and he called me to come and meet him in Chicago. I was then very young, just finished my PhD and had hardly done a year of postdoc. I went along to meet Ramachandran. And as soon as I entered his room at the University of Chicago, there were no preliminaries. He didn't say hello, he didn't greet me, he didn't welcome me. He asked me a question. Do you know what the structure of collagen is? And I honestly did not know what the structure of collagen is, and I was trained in American graduate school, so I said, I don't know. And he then fell silent. We sat in silence for about 15 minutes. Then someone else entered the room, and they said, shall we go for lunch? We went for lunch. We ate our lunch in total silence. And then I said, should I come back? He said, no, you can go. And I went all the way back from Chicago to Boston, wondering what was in store for me when I came to Bangalore a few months later. In December of 1973, I came back, joined now as a lecturer, and I entered his room once again. And now when I entered his room, I had studied a collagen. I knew that there were 1 bonded and 2 bonded structures of collagen, 1 water molecule and 2 water molecules in the collagen structure, which I was worried about. But he then asked me a very specific question. He said, you've worked with the nuclear Overhauser effect. Can you now distinguish these 2 structures of collagen by the nuclear Overhauser effect? And my instinctive and immediate response was, of course not, because we didn't even have an NMR spectrometer. And certainly we could not have done collagen at that time. But then I think this would give you some kind of flavor for the kind of man he was. And I think by also accepting Samrat's invitation to give this presentation so many years later, I have in some ways, I think, redeemed myself. Thank you very much.
So questions? No questions. Too much clarity. No, okay.
Could I make a comment? First, it was an absolutely brilliant lecture, and it was a great honor to hear it. But the other is, in this field of intrinsically disordered proteins, I remember about 20 years ago, we were trying to devise a model for a random coil. And we took the Ramachandran diagram, and we devised the model, and it fitted the NMR data we had for peptides and proteins absolutely perfectly. And so it was a great inspiration, I think, in this field as well as for globular proteins.